So before we start actually solving systems involving the three variables, I want to lay some context as to what does that third variable represent? Okay, what are we actually solving for now that there are three variables? And the one thing I want to point to is you've probably done some work with three variables before when finding like volume. If you think back in geometry, you have a whole unit involving volume, and volume is another kind of area that you'll see three different variables, right? With volume, we have length, width, and then depth. Okay, so that's essentially when we're working with systems of three variables, we're adding in that depth component into what this represents kind of uh, as an image, okay, or what it represents physically. So when we solve system with two variables, we're looking for where the two lines intersected. But once we start adding in a third variable, now these represent planes and they're not lines. Planes being like, okay, two dimensions and again, providing that depth component to it. So you don't need to write this down because I just, again, am laying kind of the groundwork for what we're solving for here. But this is an example of an equation. Um, the graph of linear equation in three variables is a plane in three-dimensional space, and that's what this is showing here. So it's essentially, if you imagine like taking three sheets of paper and finding ways that we can kind of overlap all of them, they are going to intersect at a singular point. Now, they can still intersect on a line, so our solution could be a line. But for most of the ones we're going to work on here, we're going to find a specific point that has three variables. So our solution is going to be x comma y comma z, right? Because it has that length, width, and depth component to it now that we're in three-dimensional space. When you move into calculus, the tail end of calculus, that typically ends up being calculus 3, you do a lot of work in three-dimensional space, and adding that third dimension really steps up the math quite a bit. Okay, in fact, we'll see that a little bit today, in that there's a lot more algebra involved, and thus the organization of our work is going to be so important in how we can keep track of all the things that we've done and what things we need to do. So with that, let's jump into our first example, and I have three for us to work through today. So go ahead and take a second and write this down, and I'll make sure we're all caught up to speed. While you're actually writing these down, one thing that I'm going to do that just really kind of helps, one, for me to organize my work, but especially for me to kind of talk about the process here, is I'm going to name these equations as equation 1, equation 2, and then equation 3. And so that way, I don't have to be like this equation, I can say equation 1. But it will also help me organize my work as well. All right, so with this system of three variables, we essentially have to use elimination to get started. There will be an element of substitution, but the first part is going to be substitution. And the first thing that we want to do is actually create a system with two variables. And a system with two variables means that we need two equations that have the same variables. So our first task here is going to be to eliminate one variable from two equations, and doing that twice with a different combination of equations. So the first thing that I'm looking for is there any set of equations that I can add where one of the variables will be eliminated? And if I add equation 1 and equation 3, the x's are going to go away. So I'm going to do that first. I'm going to do equation 1 and then equation 2. So x plus 2y minus 3z equals 9. And then negative x plus 3y minus 4z equals 15. And I'm going to just add these two equations together, all with the intention of eliminating a variable. In this case, we're eliminating x. So 2y plus 3y is 5y. And then negative 3z minus 4z is negative 7z. And 9 plus 15 is 24. So we now need another equation that just has y and z. So I essentially need to do the same step, but using a different set of equations. So I'm going to pick another one of these equations where I can eliminate x. So let's use, I kind of like 2 and 3. I'm going to have to multiply equation 3 by 2 to get the x's to eliminate. But But I like 3 because the x is negative, and I can just multiply it by 2 to get those x's to eliminate out. So I'm going to take equation 2, and we're going to leave that one as is. Equation 3, we're going to multiply by a positive 2. So equation 2 will not change. 2x minus y plus 2z equals negative 8. When I multiply equation 3 by 2, this becomes negative 2x plus 6y minus 8z, and it equals 30. And then once again, I'm going to add these equations, all with the intention of the x's eliminating, okay, or going away. So I have negative y plus 6y, that's positive 5y. 2z minus 8z is negative 6z, and negative 8 plus 30 is 22. Now, so we still have a lot more work to do, which is why it's really important that when you're doing this system with 3 variables, go slow and check your work. If we make any mistakes here, everything else is going to be wrong, and we're going to do a whole lot more algebra that isn't going to be correct, and it's hard to pick up on those mistakes. So go slow, double check everything, including making sure I write down the equations correctly. Okay, this is really a lot of attention to detail, so I'm going to do it real quick. Make sure that I didn't mess anything up. So did I copy equation 1 down correctly? X plus 2y minus 3z equals 9. Equation 2, or equation, that was 3. I labeled it as 2. Let's change that to 3. Good call. So negative x plus 3y minus 4 equals 15. Looks good. X's go away. 2y, 3y, 5y. Good. I think everything looks good there. Here, what did I do? 2 and 3? So 2x minus y plus 2z equals negative 8. Looks good. Equation 3 times 2, negative 2x plus 6y minus 4. Yep. And all the adding, 22, negative 6z, 5y. Everything seems to check out. I promise you that check goes a long ways. Because now we have 2 equations. I can even, let's give these names. Let's call this equation 4 and equation 5. And what we've done is we've now created a system with 2 variables, which is exactly what we worked on yesterday. And so now I'm going to take these equations 4 and 5 and work on solving for either y or z. I can do that using substitution or elimination. I'm going to go with elimination, and I'm noticing that I have a 5y in both cases. So I'm going to multiply one of these equations by negative 1 and then add them together. So let's keep equation 4 as is. So 5y minus 7z equals 24. And then I'm going to multiply equation 5 by negative 1, making that negative 5y plus 6z equals negative 22. And again, just a quick check. Negative 5y plus 6z. Everything seems to match out there. So we're essentially subtracting, but by me multiplying by negative 1, that takes care of the subtraction. So now I'm adding these, where the y's will eliminate. And then negative 7z plus 6z is negative 1z. And then 24 minus 22 is 2. And thus z equals negative 2. All right, once we have z, now I'm going to still work with equations 4 and 5, because in 4 and 5, I can plug in z to then find y. If I plug z back into one of my original 3 equations, I still have 2 other variables. So it's not going to be all that helpful. But in equations 4 and 5, because they're just 2 variables, by plugging in this negative 2, I can then solve for z. So let's plug it into equation 4. So that makes this 5y minus 7 times negative 2, and it equals 24. So 5y plus 14 equals 24. And so 5y equals 10, making y equal to 2. Now that we have z and y, we can plug these values for z and y into either of our original 3 equations to then find x. Again, it doesn't really matter. I am a little thoughtful, though, in that if I plug it into equation 1, that x is already positive. So I'll have to do a little bit less algebra to get x by itself. So I'm going to plug it into equation 1, where I can solve for x. And then I have plus 2 times the y value, which is 2. And then minus 3 times the z value, which is negative 2. And it equals 9. So x plus 4 plus 6 equals 9. And so x plus 10 equals 9, making x equal negative 1. And so our solution, again, is a point where we write it as x comma y comma z. So negative 1 comma 2 comma negative 2 is where these three planes intersect. So you can see how the organization of the work, it really helps here, okay? And this is a place that some of us need some practice with that, okay? Labeling the equations also helps. They're little things that, to me, make a big difference. Okay, let's have you all try one. I basically have 2 more problems planned for us, and then there's not any Math Excel on this. We're just going to be working on these in class today and tomorrow. Okay, so let's have you all try one. I will probably have you try the next 2, and then we'll just check them and call it a day. All right, and just to, let's make sure we all do the same thing here. So let me give us one hint. Let's go ahead and work with, is there anything that'll eliminate right off the bat? It doesn't look like it. So let's first eliminate the x's. Okay, and you're going to eliminate the x's. Let's do equation 1 and then equation 2. And you're going to have to multiply those. And then after that, let's go with equation 1 and equation 3. And again, you're going to have to multiply those as well. And the only reason I'm doing that is just that way we all do the same thing, and that way it's a little bit easier to check our work. All right? I'll give you about 5 or so minutes to work through this. I'll go over it and then do one more. Whatever time we have left, we can just hang out and chill. Okay, for those of you online, you can check to make sure that you got your answer correct. You should have -1, 2, -3. Go ahead and hit pause and check all these steps here. The one thing that might be different is if you multiplied equation 1 by 3 and equation 2 by 5. Other than that, the work should look basically the same from here. So go ahead and hit pause, check your work here, and then we got one more example that we're going to work through right now. Okay, last one. So what's different about this set of equations here? And let me get attention back up front. Shh. What's different about this equation here? There's no y. See how that might change what you should do first. In fact, maybe talk in your groups as to what would be a good way to start this and see what you come up with. I'm going to just leave it at that, and then you all work through it. So, I'm sorry, say that again. What'd you do? Yep. Okay, so what Holden's saying is he's trying to add equation 1 and equation 3. The problem with that, Holden, is the y isn't actually going to cancel out because that would be 0y plus or minus whatever y's you end up getting. So the y doesn't eliminate right away with that. Oh, if you multiply it by negative? So the z cancels out. And the x. Oh, I didn't think to do that. And that's okay. We're probably going to get the same answer anyways. But awesome. Okay, so Holden's realizing if you multiply equation 1 or equation 3 by -1, you get both x and z to go away. And then you're able to solve for y right off the bat by doing that one elimination step. Okay, that's awesome. Okay, that's more recognition than I even put into it. what I would have thought for this one being easier is our first step is to eliminate one variable, right? That's what we did with all the others. I'm noticing that equation one, I've already eliminated y. So what I did, and again, there's multiple ways of how we could have done this, is I found another set of equations to get rid of y. That way I just have x and z, and then I can solve for x and z from there. Okay, so I actually ended up doing a little bit more work than what you had suggested. Either way, we should have gotten to the same answer, being that x is 3, y is 4, and z is 5. Is that matching up with what the rest of us got? Okay. So yeah, anytime one of the variables is already eliminated, it should make our work just a little bit more easy. All right. Well, that's all that I have planned for today. I don't have